David has worked in various parts of the world, and with the UK for one, and America for another, and I think he has a fairly cosmopolitan view of things, and I guess we'll hear a bit more about it now.
Wonderful. Thank you, Larry. Thank you, Gold family. It's clearly a family business. It's wonderful to be here. There's some irony in being at a health conference talking about intelligence when last week I slipped a disc trying to move a tree. I know. So, well, my wife then moved it effortlessly. So if I'm moving around in strange ways, it's not that I'm inventing new yoga moves, it's because I'm atoning for stupidity. So I'm rather interested in what I call inverse principles. And inverse principles are like these, that in some sense, our intelligence is inversely related to the importance of a problem. Okay, that would be a good example of an inverse problem. Health would be a canonical example, where the history of our thinking about health has been extraordinarily stupid, right? We learned this morning, in fact, that perhaps the reason why some of these somewhat superstitious approaches to human health, issues of animal magnetism and bleeding people to death to rid them of their dark humors, probably have some basis in placebo effects. So after all, there was some kind of logic to it, but it clearly wasn't the logic that the practitioners of medicine at the time thought was being effective. In fact, I don't know if you're still here, in your control, the case where you have a positive placebo effect in an entirely toxic medical intervention, which is what these are. And in fact, is what I would claim most medicine still is, with apologies to physicians. The thing that we've been most stupid about, interestingly, in our history, is about intelligence itself. And so this is how we've thought about intelligence in the past. We've done things like craniometry or phrenology. Phrenology, wonderful, right? That there are 27 bumps, and those 27 bumps tell us everything we need to know about human intelligence. And my favorite, this kind of thing, the doctrine of signatures, that you could read fundamental features of human competence, nobility of characters in terms of their resemblance to noble animals. And after I learned this, I grew a beard. Yeah, well, not a moustache, I hate to add. So now, one of the things that's immediately revealing of people talking about intelligence is how stupid they are to begin with, because you can't talk about it without a theory of difficulty. It's a meaningless concept, right? It's a figure ground problem. So you have to have a theory of difficulty before you could even begin to have a theory of intelligence. And I'll give you an example. If I had given all of you, when you walked into this room, that puzzle on the left, you would have been vaguely insulted, right? And the reason why is it's not the Monty Hall problem, right? You'd get that right with a probability of 1/4, okay? On the other hand, if I gave you that thing on the right that's in your beautiful painting, you'd be vaguely intimidated, okay? And the reason is because the probability of you getting that right is like 1 in 43 quintillion, right? 1 in 10 to the 18th power. So you're not really, and so, right, it's an interesting test of intelligence. That's why the Rubiks Cube is intriguing to us. It's why it's in your painting, presumably. And when you read about men like this, who took 26 years to solve the Rubiks Cube, right? Well, it's sort of a little unjust, because I bet you there's some of you who still haven't solved it either, although you're probably not working on it every day, as this guy did. And there's a quote at the bottom. It's a typical sort of English quote, because it always has the age of the, I don't know if that happens in American papers, right? So, wife Jean, 47, as if it's meaningful, said it had felt like there had been 3 people in their marriage, right? Like, and so then you hear about a kid like this, who solves it in essentially 2 minutes, 30 seconds, blindfolded. And you think, well, you tell me, who's smarter, right? It's kind of easy. Now, the reason why the kid was able to do this is because there's an algorithm, right? There's an algorithm for solving the Rubik's Cube. It's called the God algorithm. And now, as it's 2014, we now understand that a Rubik's Cube, excuse me, from any random initial configuration can be solved in a maximum of 20 shifts. So if you do it right, from any initial randomized configuration, you can solve it in a maximum of 20. But it's also true for sports, right? serving a tennis ball at 150 miles an hour with a small racket over a net into a circumscribed area is harder than rolling a giant tennis ball over an even surface at 3 miles per hour. Okay? In fact, it's something of very interest to me, we'll get there in a second, is that really, in terms of raw computational power, that's much more interesting than solving a Rubik's Cube. So what is intelligence? I'm just going to tell you right out what it is, and it's this. And you can try and formalize it. And that is making very, very improbable things very probable. Right? Intelligence is the ability to make hard problems easy. So that's what it means when you go to someone and you say, you made that look easy. Mathematics to you is so easy. That's the essence of intelligence. Okay? Finding an efficient encoding, representation of a problem, and finding an efficient algorithm for arriving at the right solution. Stupidity is what happens when you take a very easy problem, right, and you make it hard. Right? This is bureaucracy, right? This, if you say to somebody, God, you made that look so difficult. What you're really saying is you're stupid. Okay? And I think we have to be very careful now to distinguish between intelligence. I'm very serious here, by the way. You can formalize these concepts. I really mean it. That is what stupidity is. Now, I'll give an example from the history of science. The Keplerian system for calculating orbits based on the basis function that we call the ellipse versus the Ptolemaic system based on epicycles and deference. A child with a piece of string, right, and a few pins can calculate the orbit of a planet, but it takes 50 monks with mathematics calculating conic sections to calculate the same trajectory using epicycles. This is stupid. Okay? And in fact, for the mathematicians in the room, you can prove it because you can only get to the ellipse through an infinite sum of circles. It's an infinite Fourier series. You see, so it's actually infinitely stupid. And that's the difference. This is an efficient way of doing it, and that's an inefficient way of doing it. And finding efficient encodings and efficient algorithms is the basis of what it means to be smart. So I'm now going to give you 5 ways in which we've been stupid. And I'm going to try and get through them. And it's been mentioned scale. We've been stupid about scale. How? Well, here's one example. That species on the chart, that individual, in fact, photoelectric effect, special and general relativity, Brownian motion, and the tree shrew, no mathematical physics. And the reason clearly has something to do with the fact that that individual up there has such a big brain. And as you know, there are many people fascinated in Einstein's brain. Does anyone have any water that I can... Oh, no, it's here, it's here. Ouch. Okay. Right. Tree shrew wins. All right. Okay. So that's really phrenology. I mean, it's essentially larger things. And, the problem with that is, unfortunately, is that we don't have the biggest brain. And so there are other species that we know have much bigger brains than us, and we know we're smarter. Right? And so that can't be the answer. So that's another way in which we've been clever. And so what we've realized is, no, it's clearly not absolute size, it's relative size, so we turn to allometry. We turn to scaling laws. And what we do now is we say, of course your brain's going to be bigger if your body's bigger. So it can't be that explains it, it's the residual deviation from the underlying trend. So here's body weight against brain weight, and you'll see that human beings and other species have a larger residual. So that's what intelligence is. And there's an entire industry around this that doesn't only do brain, body, but does bits of brain against other bits of brain. And the problem is, the more and more we look at it, the more we find other species, like the dusky dolphin, that actually has a larger residual than ours. So these kinds of scaling effects aren't doing very well either. So the point is, we know from engineering history that bigger is not always better. Okay? So on the left there is the SAGE computer. Some of you all know that. It was an early defense computer. It was 250 tons, 60,000 vacuum tubes, 3 megawatts of electricity, that's more than this entire building, and 75,000 instructions per second, and in current dollars, it cost 87 billion. It was obsolete the day it was rolled out of the door. That's true. Here, this machine, 4 pounds, billions of transistors, 10 watts, 80,000 million instructions per second, over 1 million times faster, $2,000. Okay? So it's not size, and it's not energy use per se, it's something else. In this case, we know what it is. It has to do with miniaturization. And there are some interesting insights from FMRI, actually, that are worth mentioning. It bears on the conversation you guys started to have. And it's that one of the great pioneers here was Marcus Raichle. And I'm not going to go over this, Joy did this, but essentially, as you know, you have the brain, you stick them in a big machine, and you look at variations in blood flow, which are proxies for metabolism. And the idea behind FMRI is that you can pick up that signal associated with increased metabolism, which is localized by cortical requirement. 10 years after Raichle started working on that, he started studying BOLD, as you know. That is the brain doing nothing. And the old view is this, right? The brain doesn't really do anything until you do something, and that's the signal you detect metabolically. But now we realize, in fact, nearly all of the energy that's being used is being used when we're doing nothing. And the stuff that Joy finds is actually in less than 1% or less than 5% of total brain energy. Okay? And so the way I like to put this is this, right? Evolution cares a lot about running and very little about group theory, right? One way to think about what makes humans special is everything that evolution didn't give a shit about, right? Because everything that's difficult is stuff that we don't actually have brain to work on, right? Because evolution didn't care about it. And I think that's eventually why machines will be smarter than us, but they'll probably take a long time before they're better athletes than us. So, okay, let's now talk about how we've been stupid about data and algorithms. So there's a lot of talk about big data, and part of it's hype and irritating, and part of it's interesting. And I want to talk about what makes it interesting. You remember in the early days of AI, we all thought, it was about algorithm development. How do humans reason? Let's build expert systems. We just have to understand all the complexities of how individuals are solving problems. And we neglected data. And I now want you to think about it somewhat differently, and since there are scientists in the room, I'm going to make you think about this in terms of phase transitions of matter. So you're familiar with pictures like this, with 2 control parameters, temperature and pressure, and everyone has, even if you're not familiar with the diagram, you're familiar with it from your life, because most of us live at about an atmosphere, and if you start increasing the temperature of something like water, it undergoes transitions from solids to liquids to vapors. So I'm going to make you think about intelligence in terms of another set of control parameters. And these are going to be data. That was a very easy one, quantity of data. And there's something slightly more complicated, which we don't need to go into right now, which is some efficiency of your algorithm. And that has phases. Some of them conjectured, some of them known. And it looks a bit like this. If you've got very, very little data, it doesn't matter how good your algorithm is, you're ignorant, right? So if you take that kid who could solve the Rubiks Cube, the reason that he could solve it is because he looked at the initial configuration of the cube and then knew precisely how to apply the God algorithm to get to the answer. If he had no input, he would have just been going forever. So ignorance is what happens when we don't have enough data. Stupidity, right, is over there. You can have as much data as you like, right? But if your algorithm sucks, you're never going to get to the answer. Okay? Doesn't matter how much big data you have, you'll be big stupid. And actually what's interesting is as you move, make the algorithms more and more effective, you move, where we are now with machine learning is really an induction. We're very good at doing discriminations. Right? Is it a face? Is it a banana? That sort of thing. But we're not very good at deduction and absolutely no abduction yet. That is generating novel concepts. That's from Peirce, Charles Peirce's concept. And what's interesting, by the way, is because of the phase boundaries in this diagram, you can actually do some interesting things with data. That is that with a rather small increase in the algorithmic efficiency, if you have enough data, you can stop being stupid. You see, and that's where big data comes in. And I'm going to give you 2 examples. Okay. So let's talk about Kasparov and chess. So many of you will know about Kasparov playing Deep Blue. He got very upset about this. And I'm very proud of this, but it's utterly ridiculously simple. Watson is trivial mathematically, right? And nearly all machine learning algorithms are simple, okay? What makes them interesting is the quantity of data they have. What made Deep Blue good is it had 700,000 games in memory, okay? And about 4,000 unique configurations of the board. That's why it won, not because it had very clever algorithms. It's actually simply, it's in fact factor analysis. It's very simple ICA-like algorithms that are developed for pulling out critical low-dimensional strategies. And of course, Deep Blue won. This was a big surprise, right? So if you have enough data, you could actually beat humans at that task that for many, many years, thousands of years, we thought was in some sense definitive of what it meant to be intelligent. So you thought, oh, well, maybe is a special case. And then something very interesting happened. Many of you might not know this. Just after he played Deep Blue, he played the world. In 1999, Kasparov played 50,000 people online at once. And it's a quite elaborate scheme, but essentially they had a voting system and they had some experts that integrated the information. And in fact, Kasparov won that just, right? And he said, when he was asked afterwards, who are you playing? He said, it was the most weird, intelligent player I've ever played in my life. It was the feeling of 50,000 people against you, actually. And why does this work? Why does it work? None of those players on their own could beat him, and it's because there's a nonlinearity in the size of the data and performance for certain problems. That phase transition-like effect I told you. So you can have, in some cases, not all, if you just have enough data, all of a sudden you can solve problems you never could have solved before. And you don't have to be clever. And why is this? A little bit, this is what I do, a little bit of maths. Since we had some sort of gene slides, I can have some sort of equation slides. And they're no more or less interesting or boring. But it's been known, actually, since the 1990s that we could build simple neural networks that were universal function approximators. It's known as the Cybenko theorem. The sum of sigmoids, thresholded units, can arbitrarily approximate some function to some epsilon value. And in the 90s, when I was doing my PhD, I did it in 95, I worked on neural networks. And they were rubbish. It was actually, we stopped using them. It was considered, support vector machines came along, neural networks were somewhat abandoned, they weren't functioning very well, they weren't really modeling human neurons. And then in 2006, Jeff Hinton came along, and he said maybe the combination of Moore's law, the vast amount of data that's available on the internet now, we never had data for training that was even remotely like this, and a little bit of algorithmic intelligence, not much, would just qualitatively change how they performed. And it did. And now, these algorithms, he got hired by Google, of course, immediately. That's what Google now uses for its human language recognition. Machines are now parity with humans for face recognition, right? They outperform humans in terms of pain detection. There was a paper some of you would have seen recently. So we're moving into a new era where many things that we thought only we could do, machines can do better. And that has to do with big data sets. And so you've seen the study, how do they work? What they essentially do is they take tons and tons of patterns, they break them down into elementary units or features, okay? So for example, faces get decomposed into lines and edges, the way that our visual system works. And there was a very beautiful study that was done that you know that Google did. They took all the images online, they broke them down into their atomic units of function, they reconstituted them, and they said, what on average is the internet representing in image? And it was cats. That is the universe that we live in, is the cat universe. I have 4, so it's... And one of the other great, in some sense, great discoveries of recent times, it's the only paper of ours I'm going to put up, and I'm just sort of sandwiched in the middle, is how you integrate tons of data into a reliable output. And this is the formation of consensus I'm going to talk about this in a little bit more technical detail in a second, but that's what makes the other thing that makes a lot of these algorithms work. You have to pool distributed solutions and turn them into a sensible strategy. And most of it's done for technical systems. We work on human and non-human systems. Okay, now let's talk about how we've been stupid about collect. How am I doing? Okay. Third, I want to get to 5. How we're stupid about collectives. We can't think well about the way in which local rules translate into global behaviors. We're bad at it. Either way, I mean, either can think, how will this rule generate a collective phenomenon of interest, or the other way around, infer the atomic rule from the aggregate. So statistical physics sort of did it for very simple forms of matter, very homogeneous things like water, sort of monoatomic things. But when it comes to what we call complex systems, adaptive, evolved agents, we're dreadful at it. And I'm going to give you an example which I think matters for policy. And it's from my, I have to put this up because it's driving me crazy. This is what we think understanding aggregating data looks like these days. We call that, people who work on these things call these ridiculograms. And because everywhere you look, what on earth is that telling me? Nothing. And yet you can't pick up a journal without a stupid illustration like that in it. It's unbelievable, actually. It's a weird, very weird, and the artist should explain this to us, it's a weird aesthetic distortion of what it means to understand. And I want to understand that, why people think that's meaningful. I'm going to show you some work from my friend Michael Kern's lab. Michael is in Penn, and Michael is a theoretical computer scientist, and he's interested in things like the graph coloring problem. And I'm going to tell you what it is. It's very simple. But he does it with humans. The idea is if you take a graph like that, it's called the ring lattice, very simple one. The idea is that you want to have neighboring adjacent vertices of opposite color. That's the game, right? But Michael does a twist on that. And he says, I'm going to give 38 people control. Each one of you gets control of one vertex. And you get to pick what it's going to be, red or green, okay? And you ask, can you solve it? And you do it with slightly, successively more complicated graphs. So this graph, you've only got 2 neighbors, right? Here, some people have 3 neighbors and some have 4. And here, some individuals are neighbors with everybody and some with only 2 or 3. This is called the preferential attachment graph. This is called the small world graph, and this is a regular lattice. Okay, and so now you ask the question. This is the key. I'm going to give you either purely local information, you only know what your neighbors are, or you know what your neighbors' neighbors are, or you have global information, or near global. You can see everything. And the idea is to resolve constraints. So once again, if this is you, you're harmonious with respect to them, but not with respect to that node. Notice that if you change, you might actually fall out of harmony with everyone else. It would be much better if that individual changed, right? And so, and here's a slightly more complicated graph, and you can see it starts getting frustrated in interesting ways. So what does he find? This is the time it takes to arrive at the right answer as a function of how global your information is. Only neighbors, 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 neighbors. With the ring lattice, that totally regular form, you get better and better and better the more you know. But if you have a complex graph, the more you know, the worse you get. So the more information you have in a complex network, the worse your performance. So this is very important insight, because you'll hear many people say, we need more information, we've got to share information. No, you don't. Okay, and so we have to be careful about that, and you hear all sorts of stupid remarks being made because people don't understand the underlying mathematical structure of the problem. They just assert based on God knows what intuition they have. Okay, we've been incredibly stupid about culture. And this is what nice to see your remark about these kind of coupled FMRI things, because it's clearly the future, and I'll explain why I think it's the future. Hardware evolution can't be the full answer to what makes us interesting. We've already established that the amount of cortical resource available to do things like play chess are essentially infinitesimal, right? And we also know that essentially other animals have exactly what we have. We don't really have, and we haven't stopped us trying to find that special magic neuron that gives us our unique human capacities. So what is it that we have? And if it's not hardware, then there's only one thing left, right? And it's software. And I want to explain to you what I mean by this in a reasonable, sophisticated way rather than a sort of naive way. I think most of what makes us interesting is the evolution of the operating system. And the operating system that we care about is culture, and I call this cultural embodiment. And essentially it works. Remember I said intelligence was what makes very improbable things probable, hard things easy. So here's Richard Feynman. He's doing two things that are interesting. He's standing in front of a blackboard that has symbols on it, because that thing helps us understand, follow his chain of logic. And he's actually gesturing, too. And they're all looking at his hands. It's rather intriguing. So one thing is that we find efficient encodings in the world. And second thing is, once they're in the world, we can collectively work on them. We can be collaborative. It's very hard to be collaborative in your own brain. And now I'm going to give you some examples of this. So this is some work from Nieder and Merton. And I need to tell you what this experiment is, because it's very interesting. Take a computer screen. You put up some number of dots. You take the dots away. You put up some number of dots. It's either the same or different by some small amount. And you ask, was it the same or different? Okay? So if you showed it just 2 dots on the screen, and then said, was it 3 or 4? It would say, no, it wasn't 3 and 4. No, it was 2. But as you increase the number of dots on the screen, it gets harder and harder to just ambiguate what was true from what was nearby. And so once you get up into the 20s, I don't know if it was 24, 23, or 20. I don't know. Okay? Do you see, everyone, what that is? And this is just a logarithmic representation of the same data. It doesn't matter. That's macaques. This is humans. I always tell people, this is very important you understand this. Okay. And I mean it. It's ethically important, right? Okay. So now I'm going to show you an experiment from Japan on chimps. It's one of my favorite videos of all time. And essentially, you can see what it is, but I'm going to tell you one more time. It is, you take chimps. What they have to do, you show them numbers on a computer screen. They have to then reconstruct in order based on the magnitude of the number. Okay? And you'll see, with a slate twist. And this requires sound, and so if you could put that up, because it wasn't very loud before. Let's see if this works. I'll play it again if it doesn't.
Memory. This footage from Kyoto University's Primate Research Institute shows a young chimpanzee taking a memory test. Not only is he reading and understanding the numbers, he's able to remember their exact positions after seeing them flash on a screen for less than a second. Apes consistently get 10 in a row correct, while humans rarely reach 6 before failing.
I could just sit down now, right? So what's going on? In terms of, and Dehaene has done this beautiful work, in terms of numerosity and number representation, we're no different from other primates. What is going on? And I'm going to tell you what's going on. It's not neuroscience. It's the OS. It's the OS, and I'll show you why it's the OS. This is the OS. Okay? Now, let me illustrate it. This is easy for a human and a monkey. This is easy for a human, but it's 1,000 times harder for a monkey. Okay? Now, what if I made you do hard mathematics with Roman numerals? You'd be stupid. It's actually Roman numerals they're stupid. They're not just bad at doing mathematics. You'd be better just waving your fingers about. What Roman numerals are good at is they're good at representing numerosity, magnitude, but they're crap for doing deduction, okay? And if I robbed you of your number systems, which you did not invent, not one of you invented, not one of you invented language, not one of you invented geometry, okay? That was given to you, okay? This is what makes you smart. Now, what is interesting about humans is that we can interface with that world, and that's what we need to be looking at. That's what we try to look for, but it ain't anything else that's special about our brain. So this raises a very interesting paradox of intelligence, and I need to explain this to you because it's very bizarre. Here is humans. Human beings diverged from our nearest neighbors about, our chimp neighbors about 6 million years ago. The hominid lineage, Homo lineage, is about 2 million years old. Anatomically modern humans, that is, if you were to go and excavate in the dirt and pull it out, you wouldn't be able to distinguish it from a contemporary human. It goes about 200,000 years back. So the nervous system that we have, is on the order of 100,000 years old. The technologies that we've built, the oldest ones are about 10,000. And most of the ones that we get excited about in this room are what? 10? 50? Order 10s. What does this mean? Right? It means that 21st century software is running on 200,000-year-old hardware. That is what it means. Now let me explain what that means in less dramatic terms. If you turned on a Trash 80 and you saw macOS Mavericks running on it, you'd wet yourself. And the reason you'd wet yourself is because it's impossible. That thing's an 8-bit machine. It was running on, it has like a 16 grayscale CRT, right? That's a gigabyte operating system. It can't run on that hardware. Our culture, group theory, is running on Paleolithic brain. And this is why the hardware-software metaphor of old is wrong, right? And so it's not like that. It's like that. And that's what we all in complex systems have been saying forever. The brain is made up of ants. The brain is made up of intelligent agents. Each cell has intelligence. And I could go on about this, maybe over dinner or over drinks. I could explain why. But that's why it's possible. It's because of this. Because we've co-developed and co-evolved with the machines that we've built. That's why that paradox is resolved. It wouldn't have been resolved if we couldn't. Okay. And I've spent a lot of time working on the abacus. I'm very interested in it. And for those who are interested, ask me later. But the abacus is an intelligence enhancer. There are technologies which do not enhance our intelligence, like the automobile. You mentioned it. The automobile is a very interesting case for me. It's a moral dilemma, the automobile, because it makes us move very quickly over even surfaces, but it also leads us to become obese and kill other people, right? Whereas the abacus is only good. I'm interested in that kind of technology. And so here's the last bit of my talk in how we've been stupid about computational culture. And I think it is the dilemma of the 21st century, actually. And we're all worrying about it. And I'll just tell you what it is, because you all know what it is. And it's this, is that are the machines that we're now building, like the abacus, are they things that we're going to co-evolve with into the future and make us more just, more compassionate, extend the range of our sympathies beyond our own stupid species, okay? Or something terrible. And I don't know, but I think we have to have the conversation now, right? Now, because we've only got 5% energy budget, and our machines have 100% energy budget, and soon our energy budget too. And, I think many thoughtful people have suggested that the signs of that risk, it's not just antibiotic resistance, right, that we should be worrying about. It's the fact that we aren't interfacing very effectively with a technium, and that some of the consequences of the mismatch in the rate constants, which relate to the speed at which we can process information, are leading to things like financial meltdowns. So we know there are many positives, but there are negatives. And I haven't heard, there's a debate out there, but I haven't heard a lot of very clever stuff said in this debate. And so for me, this is the future discussion. The NSA or collaborative minds at play. I want to live in this world, not that one. Okay? So thank you very much. Let me just thank my collaborators. They make me more intelligent.
Thank you very much for that provocative talk. We have a couple of questions I can see already up in the row there. Please, would someone go up with a mic?
Hi, thank you very much for a lovely talk. Enjoyed that a lot. I just wanted to go back about halfway through your presentation. The concept of big data, this was raised in the prior talk. You had two axes that create value, the volume of data the algorithm. And I know you were simplifying things, but I'm very concerned about this big data because it's much more complex in the sense that context that surrounds the generation of the data is critical, and particularly with biological data. If the contexts aren't comparable, the data aren't. The second thing is meaning. What is the meaning of the data? Does it generate meaning, and for whom? Because meaning is a relative concept. The third little piece that's out there, and why Watson, for example, scares me, is bias. Because it's not just the questions that are asked, it's the questions that aren't asked that are important. And as we know in scientific research, increasingly an awful lot of very important questions are not being funded and not being asked. So I was just wondering if you could just comment
I mean,
on
I
that.
think I agree with all three. You know, I mean, they're comments and they're important ones. It's not as if I have an answer to them. But I think they're extremely good comments. But I think I agree with all of them. Yeah.
God, you made that look easy.
Thank you. Good. Victory. Victory. What about that bending down bit?
Yeah, no, watch the back. Watch the back. So I'm curious if you think that we can get our computational systems to the point where they would share our culture in such a way that if they really did have these abilities, that we would get to that collaborative play, maybe including them, or is it just the NSA?
Yeah. Oh. Well, you see, I mean, I think the abacus. I mean, we have one way in which I sometimes give this talk, a slight variant of it, is in terms of monoliths from 2001, that periodically over human history, something has appeared in Arthur C. Clarke's book, The Monolith, that's acted as a kind of accelerant with respect to cognitive capability. And I think we've done that several times in our history. The slide rule, the abacus, the microscope, the telescope. I mean, all of these things are extraordinarily positive. And I think what's happened recently is that, and it was there, there was the atom bomb, right? I mean, a source of great power when you wielded responsibly and a source of great destruction. All technologies have that kind of bivalent character, but I think now, more than any other time, the fact that the technology can actually manipulate our social structure that's new, actually. And much of the data that we've been talking about is social data, actually. And so in that sense, it makes me nervous because, you know, how can you abuse a telescope? You can look through your neighbor's bathroom, right? But, you know, that's pretty bad. But it ain't that bad, right? How can you abuse an atomic weapon? Very badly. But we have huge checks and balances right in place to try and prevent that from happening. In this world, and so we were talking earlier about 23andMe, and you were exhorting us to go and... And I said, well, I was saying to Ken, I said, I'm not getting those. I don't want to give those guys voluntarily my genome. Because, and it's, you know, I'm not convinced, to be honest, that a for-profit company has my ethical interests at heart. And I think this is exactly the kind of interesting set of moral dilemmas that we face, which is clearly there are advantages. There are both potentially health advantages and kind of nerd insights, but there are also long-term potential costs and moral negative consequences. And I think we don't want to be adiabatically cooked like a frog in a pot because we can't see what negative consequences the technology is bringing to the table. So I think we just have to be more sophisticated.
Right. So IBM has moved, I won't say evolved, from Deep Blue to IBM Watson.
Yes.
They now have loaded it with clinical data as well as clinical journals and practice guidelines, and have demonstrated its ability to diagnose presenting patient information far faster and more accurately than physicians. And so I guess I'd like you to speak to that relative to your presentation.
Well, as you saw from my first slide, I'm not that enamored of physicians, so I come from a family of physicians, so I have to be a bit careful. So I think that, again, you know, like all of these things, it's not binary. It was a little bit like Michael's result on global information with complex network structure, as opposed to global information with simple network structure. Everything of interest has positive and negative valence, right? And so, So on the surface, it sounds marvelous. I mean, it genuinely does. And I'd rather, it's the old argument for why you want to go to a physician in a large inner city hospital who has seen everything as opposed to a small rural hospital, even though they might have more time to contribute to the placebo effect. But no, I mean, that we learned that today. And so, but again, I mean, I think there's a level of ethical scrutiny that's required now that might be sort of unprecedented, actually, for us as humans.
Could I ask you, you sort of hinted at cellular intelligence, and it's mentioned in your abstract.
Yes.
Could you amplify a little bit about what you mean
What I mean by that?
Like,
Yes, I can. This is my book on this topic. So I define intelligence on a three-dimensional axis. And part of it has to do with representation, encodings, a little bit like Kepler, so the ellipse versus the circle. Finding the right basis set. Roman versus Babylonian, Egyptian, Arabic. The other one is inferential capability. So what you'd think of as machine learning, so just in some sense grinding through the numbers. And the third is strategic, what we typically study with game theory. That is the social dimension of using representations to arrive at successful inference. So that's how I think about them. And I can, in some sense, qualitatively score a system in that three-dimensional space. And an E. coli is very strategic, evolutionarily. It has very limited representational capacity, right? But it does have some. I mean, it can record a gradient, it can calculate effective derivatives, right? And it can do inference, it can swim up that slope. And so in that sense, an E. coli is an intelligent species, it's a continuum. Once you have many, many hundreds of millions, billions of cells, then the representational power goes up. So I've even argued that a rock has non-zero intelligence, okay? And so I think that one of the great battles in my life has been to fight people who are categorical. And I tend to think almost anything of interest lives in the real number space. And so it's a matter of, everything of interest is a matter of degrees. So that's the sort of...
Okay, we must move on. Thank you very much.